First of all, I'm very glad I was able to present or will be able to present at AAIC 2022. So I'm sharing my work on network neuronal hyperexcitability. And what we see in Alzheimer's disease is an imbalance of excitation and inhibition. So this manifests in several phenomena that we can see in clinical patients, such as hippocampal hyperactivity, which has been well described in the literature, cortical hyperexcitability, the risk of seizures. So all these have been associated with this imbalance of excitation inhibition, where when you tip the balance, you might end up with getting seizures, for example. So the work I'll be presenting is mostly preclinical. So I'm working with animal models of the disease, looking at two different types of Alzheimer's disease mouse models. So in one case, I'm looking at the APP-PS1 mouse model. And in the other mouse model, I'm looking at the APP knock-in model. So the main difference between these two that I wanted to explore and understand was whether the protein overexpression that we see in the older mouse models of Alzheimer's disease, which are the APP-PS1s, is protein overexpression. So this has been associated with neuronal network hyperexcitability. This can be sort of considered an artifact of the model, which is where the APP knock-in model comes in. This newer model, attempts to address some of the issues related to protein overexpression, allowing us to get a better picture of whether protein overexpression is actually confounding the neuronal hyperexcitability that we see in animal models. And to this end, I've characterized quite a bit of the animal models in terms of epileptiform activity and changes in power spectra, for example. Most interestingly, what I found so far is that the APP knock-in model does not appear to exhibit clear signs of network neuronal hyperexcitability, which is sort of suggesting that the protein overexpression that we see in the older animal models of Alzheimer's disease may actually be contributing towards an artificial presentation of neuronal network hyperexcitability, which is technically what we don't want to see when we are using an animal model. What we want the animal model to be is a very faithful replication of the human condition. So in that sense, perhaps we do not have a model of network neuronal hyperexcitability at the moment. So based on what I mentioned with regards to the findings, this also suggests that because we don't have an animal model capable of representing hyperexcitability in a way that we can use for drug testing or use for any therapeutic interventions, we might have to start developing a mouse model that accurately mimics the human condition. So in this regard, we also need to consider several variables or several aspects of this model, whether the hyperexcitability that we see is in the correct brain region, or the hyperexcitability comes at a certain progression of the disease. These are some of the factors that need to be considered. And there are certain lines that we would like to try and follow to see whether we can sort of develop this mouse model. So what we are also looking at is, in the APP knock-in model, there is no mutation in presenilin, which might be an avenue worth exploring to incorporate into this model and to characterize the hyperexcitability to see whether it's actually a better model of Alzheimer's disease and neuronal network hyperexcitability.